Good, we're all here. Okay, this is our last lab of the year. This is the lab where we're going to do a campus tour. And we're going to see what we can see in terms of geology on campus. I'm glad you all can make it. It's a beautiful day, 70 degrees here. I mean, as you all know. But one of the things I want to do today is when we visit these different places, I want you to use that most famous word in science, look at things, see if you can have some questions, and then we'll talk about it. I know Bobby Joe and Betty Jo Bielowski, that famous brother and sister team that has been here all semester, will probably ask some questions. But it's going to be based on a lot of the concepts that we talked about. And then we'll also do, hopefully, a little bit of critical thinking along the way. The only thing that's going to be different about today's tour is I'm feeling kind of lazy. I got a teleporter. So what I'm going to do is I'm going to push this button instead of making you guys do all that walk all the way to these different sites. This is just going to propel us to these different sites. So let me see how this works. 1, 2, 3. Okay, go folks, pick it up. Geology pace, we don't have all day. So here we are between the science building and Coffrin. They're digging a big hole here. They're putting in some sort of air conditioning thing. What do you see when we look down over across the way? Besides an awesome digger I'd like to play with, but they won't let me. What I'm most interested in, if you can see it, there's a layer of clay on that vertical ledge there. And, ooh, I said clay, darn it. So it's clay. What does that tell us about how that was deposited? What was the energy of the environment for that clay to be deposited? Anybody? Anybody? Bobby Joe? Betty Joe? No? Okay. Oh yeah, there we go. So it's a real low energy. In fact, it's an ultra low energy of the environment. And with clay particles, we're probably talking about a very still body of water. And when I look at it here, that clay is upwards of 10 feet thick. What's it doing here? Is it possible that it overflowed the Fox, but it's a floodplain? It's possible, but there's an even better reason, and that we'll talk about next week when we talk about the geology of Wisconsin. We're standing in an area during the Pleistocene that was known as Glacial Lake Oshkosh, a huge glacial lake. And you had all this runoff from the glaciers and all the silt and clay washing into the lake, and it settled out and formed a very thick layer of clay. And is clay an aquitard or an aquifer? Right, aquitard. So it holds water near the surface. So anywhere in the Fox River Valley, where it's flat anyway, there's no sand and gravel, and it holds the water to the surface. And that's why whenever it rains around here, it's muddy, etc., etc., etc. The other thing that's pretty cool is it's red. And when we do the geology of Wisconsin next week, I'm going to tell you where the red came from. It's iron, but where did the iron come from? Hey, a little better pace that time, even with the teleporting. So I'm standing here in the road, which is not atypical for a geologist. We tend to stand all sorts of crazy places. But I happen to notice something right here. Exactly. I know you folks from Chicago, Milwaukee have seen these potholes. Well, how did that pothole form? Do you remember? Correct, ice wedging. Ice expands by water expands by about 10% when it freezes, and it does so with the pressure equivalent to dropping a bowling ball about from your waist down to your big toe. So not all potholes form that way, but it's really, really common that they can form that way. You do find potholes in different parts of the world for different reasons, but this is the most common one in Wisconsin. Well, here we are in the grotto. Colorworks family grotto, and it's beautiful. If I had my acid bottle with me, I forgot it. I could pour acid on these bricks here, not bricks, but pieces of rock, and it would fizz. So that would be the mineral calcite. Very good. And if I looked real carefully, I would see fossils in at least some of these pieces of rock here. And we're going to talk more about that later. But limestone is a very common building material, building stone. We'll also talk about that later. Gorgeous day to be out by the river, the Mighty Fox. I just read in the newspaper where they're finishing up cleanup of the Fox. It's been a 12-year project. It's a super fun site, one of the most contaminated sites in the United States over the last 12, 13 years. They've been cleaning it up at a cost of over $1 billion. They should be done this summer. What they're doing is removing PCBs, which are organics. They take the sediment on the bottom, they burn it, which makes the organics harmless. And then they put it in a landfill, and then they put a layer of sand on the bottom of the river. Was pretty controversial, but again, the Mighty Fox. We'll come back to that in a second. What I'd like you to notice here, we're back in the science building around the corner from the grotto. Notice how up here, there's a level where the parking lot is. It slopes down. There's a level here, slopes down to the river. And if we looked across way to the other side by the school building over there, you can see the same thing. There are different levels, and those are called terraces. And those terraces represent times when the stream was at that level for a regular period of, or a longer period of time. And so if we look up here, once upon a time, the Fox River was as deep as where the parking lot is. Then it changed to down here and stayed here for a while. Now it's in its current location. Where did all that water come from? When did these terraces form? Again, that you can see across the way there. When did these terraces form? Where did all that extra water come from? So we had a much, much bigger Fox River. Is there anything in the last 10 or 12,000 years that might hint to a higher water level? Betty Jo, absolutely. When the glaciers melted 12,000, 11,000 years ago, all that water had to go somewhere. And it filled in and made a much, much bigger Fox River. And then it drained down to a level, sat there for a while, and now it's where it's at right now. And if we looked at the Fox River, remember, right here the water is less than 5 feet deep till you get in the middle. Then you have a semicircular channel. You get on the other side, it's about 5 feet deep again. So you have 1/3 5 feet, I don't know, 8, 10 feet, something like that is the channel, is 1/3, and then it's about 1/3 5 feet on the other side again. If the level of the Fox River decreases significantly, where these shallow levels are here now will be the next terrace. So there'll be one more terrace when the river gets lower, if it ever does. It's brown in the Fox River. It's brown because there's red clay in it. Where'd the red clay come from? We just saw behind us where the red clay was. We said there used to be a big lake here. The clay settled out on the bottom, and now when it rains, it washes off any open areas where that is exposed. Springtime, lots more flow here. If I came out here with a bucket of sand, gravel, silt, and clay and threw it in the river, the pebbles, cobbles, boulders would sink straight down. The sand might just go down a little ways and settle. The silt might go, gosh, maybe a few hundred feet, a few thousand feet and settle. The clay is going to go all the way out to the mouth of the Fox River and to Green Bay. And there it will form a delta. Not as neat and cool as where they got the jazz music in New Orleans, but nonetheless a delta will form out there. Pretty cool stuff here. We don't really have a floodplain per se, except for this area right up in here, but we don't see all the features of the floodplain because of human activity. Okay, you folks might remember this building right here. This is Main Hall. We're in back of Main Hall, and we're by the statue of Jesus here. And this statue was donated by the class of 1934. So this has been here for about 86 years. And if you come up close, you might see some sparkles, maybe not. Those are crystals. But you'll certainly notice that it seems Jesus has lost some weight in the last 90-ish years. Why is that? Why is he sort of fading away here? Nothing to do with religion. Why is that, folks? Correct. If I poured acid on Jesus, he would fizz. Jesus is made of marble, and marble is the mineral calcite, so he would fizz. But where did the acid come from? Have people been out here dumping acid on Jesus? I don't think so. That's not a very good idea. But where it came from, naturally and contributed by humans, is carbonic acid in the atmosphere. And rainfall is slightly acidic because of that CO2 mixes with water. And even before humans were on the scene, rainwater was slightly acidic because we breathe in oxygen, we breathe out CO2, combines with moisture, produces carbonic acid. It's been increased because of the burning of fossil fuels. In fact, one of the guys, when I was in graduate school, did a study, and he went to a whole bunch of grave sites out on the East Coast, and he looked at people that died as far back as 1750, and he did 25-year increments and looked at tombstones, and he could tell when acid rain increased by looking at how much these statues have dissolved. And it really picked up about 1840 is when acid rain was really significant. Does anybody know what was going on? 1840? Correct, the Industrial Revolution. And there they cranked out a whole bunch of sulfur. So now you had sulfuric acid and carbonic acid both dissolving things. There's still a little bit of sulfuric acid today, but not so much. Today it's primarily carbonic acid. We've done a nice job of removing sulfur from power plants, coal-fired power plants and stuff like that. But nonetheless, pretty cool. If this statue was made of, by the way, if you stick around for a few tens of thousands of years, the statue will be gone. It'll completely dissolve away. If this statue was made of granite, you might need to stick around for a few tens of millions, maybe 100 million years, and that'll be gone because of hydrolysis, that other weathering phenomenon we talked about. If this statue was made of quartzite, you can go back a billion years from now, it'll still be sitting here nice and cool and neat. So if you want a statue in your memory, get out of the quartzite. But it costs a lot more to carve granite and quartzite because it's a lot harder. Calcite's about 4.5, and they're all up around 6. So you need a heavier blades, more expensive, etc., etc. But again, kind of a neat little instance of geology on campus. Hey, you're keeping up. Great. Okay, so you might remember this is Main Hall. This is St. Norbert College. And let's just take a look at these steps. We did this once before, but let's take another peek here and see what we can see. What do we see up in here? Wow, looks like a whole bunch of fossils. Look at these over here. Boy, they really stand out. What's that called when something weathers at a different rate than something else? Correct, differential weathering. So for whatever reason, these fossils are a little more resistant than this limestone is. So this would fizz as well. It's not marble, it's limestone. So when we go on our field trip, I tell people that that this is about 400 million years old. And then some wise guy from the crowd, or wise person, sorry, always says, well, how do you know that? You can't age date sedimentary rocks. And I say, good one, Petty Joe. And I said, how do we date this? How do we know this is 400 million years old? Next week when we do our Geology of Wisconsin, you're going to find out that the youngest igneous rock, the youngest rock we can date in Wisconsin without carbon dating, is 1 billion years old. And this is much younger than that, so how do we know that? What they do, what we've done, not me, but we've taken a look at all these fossils. And we found out that that same assemblage, that same group of fossils occurs over in England. So we know they're the same age because they occur over there, the same group. And over in England, they have dikes that cross-cut the limestone. And so we use cross-cutting relationships, age dating, and fossil correlation to date this. And again, this is about 400 million years old. The other thing the fossils help us with, this rock formed in a warm, shallow, tropical sea, and it was mined quarried just a few miles away from here. How did we get a warm, shallow, tropical sea 400 million years ago? Well, if you recall, we were just starting to construct Pangea at that time. And at that time, what is currently Wisconsin sat about 5 degrees south of the equator, and it was in a warm, shallow tropical sea. Think the Florida Keys, think the Bahamas, think Australia, where you got the Great Barrier Reef and stuff like that. So all of this stuff settled to the bottom, fossils were preserved, and Wisconsin, North America, has since moved about halfway from the equator to halfway to the North Pole. We're about 45 degrees, just about halfway to the equator. So lots and lots of cool principles we talked about we can see right here. There's one other thing I want to point out. Here's a pillar that holds this up. What kind of rock is that? Great big pink crystals. There are round crystals that are gray. There are white crystals here. There's some black crystals in there. The black crystals are biotite. Anybody know what the big pink ones are? Correct, orthoclase. There's gray quartz in here, and there's plagioclase. Big crystals formed above ground or underground. They're phaneritic, they're plutonic, and I know y'all got this. This is a granite, and they use granite for lots of different cool stones. This particular granite, I believe, came from the Minnesota River Valley, and is about 2.5 to 3 billion years old, something like that. They mine it real commonly down there. If we were allowed in the building, you would see that the steps here are composed of slate. I wonder if it's open. Nope, they won't let us in. But it's composed of slate, so they use slate as well for building material. So lots and lots of cool things here. Okay, we didn't move too far. Getting old, legs getting tired. But let's look again at Main Hall. What color is it? Right, it's red, brownish red. And they're bricks that make it brownish red. And how do you make a brick? Basically, you take clay and you fire it. Not exactly, but pretty close to that. And these bricks were made locally. How come they're that reddish brown color? Exactly. Remember back to stop number 1, when we saw that all of this area down to 10 feet or thereabouts, maybe more, is the red clay. They mined that and made the bricks. So these are all locally made bricks that we see right here. And one of the things that geologists do, we have lots of different hats that we wear. One of them is called an economic geologist. And actually that's what I did my master's degree in. And an economic geologist is a person that goes out and tries to find gold, lead, silver, copper, oil, limestone or granite to use it for that, etc., etc. And let's just look around now at some of the uses of geologic materials. All the sidewalks are made of cement, and there's a lot of pebbles in there, some of them, but there's also a lot of crushed up limestone for cement. When we looked at the road out there for asphalt, they use tar, which is derived from an oil product, and then they mix it with some gravel and make asphalt to pave the roads and stuff like that. This flagpole right here, this flagpole was mined. It's a metal, and it's probably got 4 or 5 or 6 different varieties of metal in there. Steel has 1,000 recipes, so if you want graphite steel for golf clubs, it's a little stronger but more flexible. If you want a cheaper one, you can just get a chunk of steel that you might use for an anchor on a boat or something like that, but 1,000 different recipes. As we swirl around here a little bit and we look, I want you to consider everything that you see was either grown or mined. If it's not wood and it was constructed by humans, that means it was mined. So there's a heck of a lot of mining. Ooh, the bell! There's a heck of a lot of mining went on to build this campus. Now extrapolate that and think about the Mall of America and the big cities. Just think about how much mining occurred to build the civilization that we have. And this goes back to critical thinking. And this is where I wish we'd have had more one-on-one time together to spend more time thinking about critical thinking. Is mining good or bad? Betty Jo? Absolutely correct. Define your constituent. If I own a mining company and I'm getting rich, mining's good. If I'm some of the local inhabitants, the plants or animals, it's not good. Except for the other plants and animals that still survive. But we can't subsist without mining. Mining is a destructive process. Destructive isn't good or bad. Destructive just means it displaces things, it causes damage, but the damage is not good or bad. Sometimes if you dig a hole and make a swimming pool, you might consider it good. But it's a really interesting concept to think. Again, wherever you're at right now, look in your room, look out the window, think about the city or towns you might have driven through. Everything you see was either mined or grown, and most of it was mined. When we do our campus tour, I also give about a half-hour discussion of distribution of resources, and it's pretty hard to do without you folks in person. But keep this in mind, that 20% of the world's population consume 80% of the resources. We're the lucky 20%. 80% of the world doesn't have nearly what we have. They're still struggling for water. They're still struggling for housing. They're still struggling for health. Lots and lots and lots of things. So even in this coronavirus nuisance, nonsense, horror, terror, whatever you want to describe it, we're still so much better off than most of the world. And we spent some time saying, well, what's the solution to that? It's really, really difficult, and there really, really isn't a good solution. If we do more mining, cause more pollution. If we give away half of our resources, we would have half as many computers, half as many people going to college, half as many cars, half as many laptops, half as much food, half as much medicine, and that only increases the rest of the world by about 15%, so they'd only get 15% more. Really bad equation that needs to be solved someday. Hopefully the pandemic will do it by reducing population. But in any case, this was our virtual tour. There are more stops we could make, but I know you guys are getting tired. I'm getting exhausted. But geology is way cool in so many applications. So good to see you all here. Good to see you